So, kind of to quickly review some of what we did last time, I kind of laid out the idea of a set. And I want to point out something about this class. Some of the stuff we're going to talk about is going to be deeper than anything you discuss directly with your students, because this class's purpose is not just how can you teach concepts, you also go deeper into the way students develop those concepts. Does that make sense? So we will do stuff in this class that you will never try to teach to some little person, right? That seems to sometimes get confusing for students. So some of the stuff we're going to talk about today, again, it's not stuff for like second, third graders necessarily. So that is a set. Use the brackets for the set. Is it a finite or an infinite set?
Finite.
Finite, because there's a certain number of terms, a finite number of terms. It doesn't go forever. How big is the set? What would you say? The number of things in the set? Three. So there's an idea of number, and there's an idea. There's the numeral we use to capture that idea. 3 is an idea. The numeral 3, even the word 3, is what we use to capture that idea. Does that make sense? For example, we're going to learn this officially later, but here's how the Mayans would write the number 3. Here's how the ancient Chinese would write the number 3, right? Here's how the Babylonians and the ancient Chinese would write the number 3. Do you guys understand? Those are all capturing the same idea with different numerals. The numeral is the symbol. The number is the idea that it captures. Is that cool? Maybe. So, have I said this phrase yet? Do you guys know what our numeration system is actually called? Yes?
Hindu-Arabic.
Hindu-Arabic. I love it. So we, like so much, our language, our numbers, we basically stole or borrowed them from other cultures, right? So Hindu-Arabic is the numeration system we use. So one thing I like to tell students, stuff like the square root symbol didn't have to look like that. But it's even more basic. The number 2 didn't have to look like that, right? We just, at some point, somebody said, what about this? Yeah, it looks good. Okay, everybody, this is 2 now. You know? You guys kind of with me? Okay. All right, so coming back to this. We have the idea, we have a set. You can talk about the number of things in the set, and that is captured by the numeral 3. Number, numeral. Let's see. What do you call each of these? So one piece of a set, there's a certain word, it starts with the letter E. Element. I like it. So these are the elements of the set. And I think last time I showed you some symbols like this one. Is that a true statement? What does that say? A is in or is an element of set A, right? So what's really cool about that little thing, it looks like a little E, and it does stand for is an element of, right? How about D? Is D an element of A? So then how can I say that? So that's not true, correct? Yes. Yeah, we're so creative. Math people. We're like, ooh, put a line through it. Yeah. Okay, nothing too ground shaking yet, right? Last time we also talked about comparing sets, like if B was A, B, C, D, how do A and B compare? So you can compare them in a few different ways. The number of things in A versus the number of things in B. How do those compare? This is all, you know. This is nothing tricky. Just what is it? Number of things in A. How does it relate to the number of things in B? They're different. How? Be specific.
Value of the number?
No, just which one's more? B. So then the number of things in A is less than the number of things in B. So the idea of ordering numbers is something that children have to develop, right? So for example, what do you think is the first real connection with numbers that children have? There's a lot of different answers you can give to this, but like in an educational setting.
Probably blocks.
Okay. Even before that though, I mean, how can you identify the number of blocks if you don't know what the number is? If you don't know what 4 is or whatever. So what do you think what's the very first thing that they do with letters?
Just learning the alphabet.
A, B, C, D, twinkle, twinkle, yeah. Right? So what's the very first thing we do with numbers? 1, 2, 3, 4, 5, 6. Yeah. They memorize the chant. Are you guys with me? So being able to recite those doesn't mean you understand numbers at all. It's just a little song, you know, yeah? Just like ABC. Can you re-say that? Does that mean you can spell anything? No. You guys kind of, but it does set up these words. Then we're going to give it some meaning. Does that make sense? So very often children learn about things like letters and numbers from chants first. Now you also can argue that they hear it in language used in the home and so forth. They hear the numbers, but those even have less connection with anything. Right? Okay. All right, let me kind of rein myself in. Yeah. So last time we also talked about if I want to relate the sets, what symbol can I put in the middle? Are they equal to each other? No. Who remembers what the symbol is I could use in the middle? I can actually use 2 different ones. Sort of, but what's different about it?
You put the line underneath the...
And it's not a less than, right?
No,
It's soft, yeah, okay. So A is less than B. A is a subset of B. So I could use that, or I could put a line, because those are both true. This means it is a proper, poor little markers, proper subset. So a proper subset just means it's not equal to it, right? Okay. So I could, this is also true, because that's is a proper subset or is equal to. So it could be either one. Since it's a proper subset, that is still a true statement. I like it. Now, how are we doing so far? Nothing too major, but some stuff you're not used to saying these kind of words. You're not used to talking about stuff in this way. But what if I give us one more set? Okay, doesn't mean you do that. Sure. How does C relate to either of the other 2 sets? Yeah.
The number of A is the same as...
Kick ass! So A is not equal to C. You guys agree with me? A is obviously not equal to C. But there is something the same about them, correct? And of course, all of us know there's freaking 3 things in each one, Jeff. Okay, great. So if I want to get really technical, I cannot say A equals B because they don't have C, because they don't have the same elements. But I can say A is equivalent to C. That captures the idea of how many elements there are in each. Let me stop for a minute. So equivalent is more a measure of, do they have the same number of elements? Equals is they have the exact same number and the exact same elements. Okay. I like it. There's also this idea of, so here's what I said earlier. Certain things you're not going to tell your students, but they are ideas we have to understand. There's something called a 1, So one correspondence. Before I even describe what that means, do you think that there's a one-to-one correspondence between A and C? So what might that mean? One-to-one correspondence. If A goes to D, B goes to E, C goes to F, did it leave anybody out? One-to-one correspondence, right? You guys with me? Real quick, here's a little something interesting. If I put, do you have to count those, or can you tell how many there are just by looking at it?
You can tell.
How many dots are there? 4. Holy shit, yes. And why are there 4? Because there's a one-to-one correspondence between each dot and the numbers 1, 2, 3, 4. There's a one-to-one correspondence. That is a way deeper idea than any little kid needs to know, but that's us realizing that's how our brain maps shit, right? Do we have to directly think that way? No. Is it important for you to know that's how your students are mapping things out? Yes. See, this is what I mean by, you're never going to tell, okay, one-to-one correspondence. No. But you're going to know that's how they're putting this stuff together. We're not born knowing what the hell 1 and 2 are. We have to map this shit out. Even language. I got to map chair to this, word to object, right? Okay, sorry. I'm not going to become a language teacher. Shoot, I was going to do something. Oh, that's right. What if I put, now, a little side note. Do you have to count? No, you might have listened to the, can you just look at that and tell, or do you have to actually count? Yeah, so it's interesting that up to about 4, maybe 5, depending on how it's situated, we don't have to count. After that, we do. It's interesting about the hardwiring of the brain and what it's capable to do. In fact, a lot of ancient civilizations, really ancient, they only had numbers for 1, 2, 3. And then there was a word for many. Because overall, they didn't have to worry about 50 million. They just need to worry about how many cows we got or whatever, right? How many rabbits did you catch for dinner? Many. Oh, good, right? Okay. So the idea of one-to-one correspondence, I can create one between these sets. A corresponds to D, B corresponds to E, C corresponds to F. Therefore, they are equivalent. Another way to say that is they're the same size. Let me ask you a really funky question, though. I'm not going to wait for your permission. I'm going to do it anyway. What kind of set? Well, this is not the funky question yet. Let me see. What have I not used? F. What kind of set is this? Can anyone tell me anything about that set?
Infinite.
Infinite? What kind of numbers are those? Natural numbers, kick ass. All right, what about this set? Good, even natural numbers, and it is also
Infinite.
Can anyone tell me which one's bigger?
The same length.
I would understand if you said F was bigger. Because doesn't F have all of this in it plus other things? But if I can find a one-to-one correspondence, doesn't that mean they're the same size? Yes? How do I go from 1 to 2? What do I do mathematically? How do I go from 2 to 4, 3 to 6? I keep doing what?
Squaring.
Multiply by, not squaring.
2. Oh.
2. Multiply by 2, right? If I did that to every element in here, would I not get every element in here? Is there a one-to-one correspondence? Here, let me try this again. Is there a one-to-one correspondence between these elements? In fact, we know exactly what that correspondence is. It's that, right? Stay with me. Don't freak out. Do not freak out. This is weird. You guys know infinity's weird as shit, yes? Everybody knows this. You ever heard the thing about if you had a hotel with an infinite number of rooms and they were all full, one more person comes in, can you make room for him?
No.
Yes, you can. Tell the first guy to move to the second room, tell that guy to move to the third room, and then forever. There's room now, right? So infinity is weird, okay? So infinite sets, countably infinite sets, are the same size in a way, because there's a one-to-one correspondence, okay? That is definitely beyond anything you necessarily want to talk to your kids about, your future students, all right? So I just want to reinforce the idea of one-to-one correspondence. I wanted to give you an example of a situation where you can actually figure out a formula for it. If I double this guy, I get this guy, correct? So that's the one-to-one correspondence. Okay. Maybe. These are both infinite sets because they keep going forever. Okay. What was the one last thing? There's one last thing. Oh yeah, that's right. Have you guys, I don't know, when you took algebra, can you guys remember when you took algebra and you would solve an equation, did you ever have to give a set of answers? Like if there's more than one answer? Do you remember what you did when there was no answer to an equation?
No solution.
You'd either write no solution. Oh yeah, go ahead, say it.
0 and then a line.
0 then a line, a kick-ass. You know what that's called? All right. Ain't no damn answer. No. Anybody else? So you could also do this. If you had to make a set of all the answers and there are no answers, you can just give this. What is this? This is a set with how many things in it? So what kind of set is it? Good. So these are both symbols that mean empty set. Empty set, empty set. So be very careful. I have to tell students in some classes that right there 0 with a line, I say don't do that because to me that means no solution. When the answer might be 0. Do you see what I mean? So these both mean no solution. Shoot, I erased it. Yeah, that's coming up. Okay, good. We'll do that in a minute. Yeah, I don't think that's till later. Yeah, it comes up in a minute. Okay. Yeah, there it is. Okay, beautiful. So Venn diagrams. Somebody said something about Venn diagrams. Let's take a look at those. So if I went out, I don't know if anybody's, if I went out and I talked to people over 21 and people under 21, and I asked them if they were, what political party they kind of lined up with the most, right? Is it possible I could get people that are less than 21 who are also Democrats? Yes. Would everybody less than 21 be Democrats, more than likely? No. So if I draw the Democrat circle, if I put it here, what would that mean? If that was Democrats. Were there any Democrats I talked to that were over 21?
No.
Where are the people who are over 21 in this picture?
On the outside.
Like right here, right? That's out here. Anybody in this circle is less than 21, so anybody outside of this circle is over 21. Are you guys with me? You guys have all seen Venn diagrams before, is this true? Like a standard Venn diagram looks like this. Right? Okay.
Do we have to have the square around it?
Yes. And here's why. Well, okay. In some cases, you don't need it. But the reason I do agree with putting it there is because it represents the universe, right? So some people don't want to put it there because like the universe is expansive, right? And I'm like, I don't. So this is the universe. So are there Republicans in here? Yes. Where are it? Who's this person? Tell me everybody, anything you know about that person. They are under 21 and they're not Democrat. Does that mean they're Republican?
No, because they.
Okay, how many political parties are there?
Near it a bit.
Huh? It's stupid.
But
Do you know there's over 1,000 people that were running for president in the last election? Did you guys know this?
No.
No. There's at least 53 political parties that I know that had enough people that actually got on some ballots in certain states. 53 political parties. So obviously you have your big ones, Republican, Democrat. And then you have, what's another one?
Libertarian.
Libertarian's a big one, you know, and they always have somebody's in jail or whatever. So their candidates running from jail. This happens often. And then you have, like, you guys know about the Green Party? I think Jill Stein was in the Green Party. Believe it or not, there's still Whigs. There's Communist Party here in America. There's the Socialists. There's the Democratic Socialists. It's insane. Then you get the really wacko ones where the main candidate's wearing all this weird shit, and you know, he's like, wow, okay, huh?
Red's too damn high. That's what
Yeah. Red's too damn high. Yes. Okay. So how should this probably look? If I talk to students and I ask them their age and I ask them what political party they are, it should look more like that, correct? So this would be like the Democrat circle. So this person right there, what's true about them? Yeah, they're a Democrat and they're less than 21. Right? And you're like, I like how you emphasize random words, Jeff. The word and is silly important there. What's true about this person?
Above 21.
Yeah, they're older, they're at least 21, and they're a Democrat, right? Okay. You guys get the basic idea of Venn diagrams, okay? Where they get challenging is when you're given specific numbers that match certain regions, right? This is where things get challenging with Venn diagrams. So for example, actually before I do that, let me do a few more little definition kind of things. Yeah, I need some new markers. Does anyone know what this region here is called? What do you think? Is where those two circles do what? That's where they overlap, it's where they converge. What's another way you could say that? Okay, kick ass. Not quite what I look, but I love that you know the word. This is not quite the union yet. When I see a street and then it meets another street, we call that the intersection. Okay. So this is the intersection of the two circles, right? If you are in there, let's say this is you like apples and this one is you like bananas, right? If you are in there, what do you like? So you like apples and bananas. Good. So this would be the intersection of A and B. That's a lot of words for a math person, so we use a symbol. The word that goes with this is and. If you're in there, you must meet both circles' requirements. You do this and you do this. So A and B. And the symbol we use is kind of cool. It looks like a letter A that's been rounded and it lost the middle bar. So if you draw like a rounded A, but then you lose the middle bar, that's and. That's A intersect or A and B. Kick ass. So these people would be under 21 and Democrat. That's the intersection of those two ideas. How are we doing so far? Now, the word that came up a minute ago is union. If I take one group and I make a union with them in another group, do I only take people that are in both groups, or do I get everybody from both groups? Everybody. So the union would be all that. That's A union B. If you're in that union, what do you like? No.
You like
Nope. Is this person in the union?
Yeah.
What do they like?
Apples.
Is this person in the union?
Yeah.
What do they like? So if you're in the union, you like apples or bananas. So the word for this is or. And I love the symbol because if I'm like, you or you, somebody clean the room. You. Right? Freaking somebody clean the room. I don't care, you or you or you, just somebody clean the room. That I don't know if that helps at all. I don't know. So that symbol there, or. Who's seen those symbols before? Anybody? Very often, if you've taken any probability classes or anything, you've seen those symbols. Okay. So let's do this. Let's step away from Venn diagrams for just a moment. Let's do some very pointed practice problems with these two ideas. Yes?
I have a question.
Yeah.
For the A or B,
Yeah.
isn't it A or B or both? Because it's also the middle? Or
This is a very good point. You have all different kinds of ors. So if anybody's ever done any computer science, you have exclusive or, and you have all these or. A or B, the way that we use it, it does mean or both.
Oh.
It doesn't mean exclusively or. So if I wanted to say A or B but not both, I'd have to say exclusively or. Yeah, does that make sense?
Yeah.
That's a good point, yes.
And if it's not filled in the middle, would that mean excluding?
Beautiful. If it's not filled in the middle, that's the exclusive or. Supposedly it feels good. Okay. So let's do some something that's not looking like a Venn diagram. Let's see. So what would A intersect B? B. Oh, okay, sorry. I didn't realize you were actually answering the question. Yeah, so intersect means the answers have to be in both. So here's what I like to think of. And is the mean bouncer at a club. Let's say I go to a club, come to the door, and they say, okay, to get into this club, you have to know Joe the bartender. I'm like, I know Joe. And he says, and you have to be rich. All right, shit. And you have to dress nice. Shit, all right. So I can't go in the club, right? So and will always reduce the number of things that can be in the answer. Does that make sense? Have any of you guys ever applied for any kind of scholarships or something? So I remember back in my day, kids, we used to have this, the financial aid office had this giant book of scholarships, and you come in there, and it said, to get this money, you must be a math major. Check. You must have this GPA. Barely. And then you keep reading, and at the end it would say, you must be
Tall.
1/4 Cherokee Indian or something. Next page. So the and, you have to meet all the requirements, fewer and fewer people. So the intersection will always be a smaller group. So what's in both? Like you said, only B and Z are in both. What about A or B? Yeah, so A, what I like to do is this. A or B has to include everybody. So I write one of them, A, B, F, Z, and then I go, okay, who's new? Do I have B already? Yes. W is new, X is new, Y is new, Z I got. That's everybody. Yes?
Oh, do we not have to keep them in like a order?
No.
No, okay.
It's like me saying you, and you come with me, but if I go you, that's still the same group of people. Yeah. So again, this one I remember is like, somebody do this, you or you, I don't care. Yeah, okay. Oh cool, okay. So visually, we've got these ideas, right? The intersection is where the two circles actually meet. The union is just everything shaded in together. Oh, let me do one more thing here, yeah. So on these kind of problems, I'm also going to give you a universe to live in. So let's say in this case, the universe is, let's see, A, B, F, W, X, Y, Z. Okay. So that's the universe, right? And actually, let me go careful. Let me go further. M, N. There's the universe. Okay.
These like random numbers that letters you're popping up, or?
Yeah, like if you're talking about Grossmont students, your universe is Grossmont students. A subset could be Grossmont students who are taking Math 125.
So these are, that was the gross one.
So these sets live in this universe. Does that make sense? So for example, you guys are a subset of Grossmont students, correct? Hopefully, or else I don't know what you're doing, right? So Grossmont students would be our universe. You would be the set A defined to be students taking Math 125, who showed up today, I should say also, because there's more out. Okay. All right. So what would this be? What do you think this would be? Universe minus A. Let me just throw this at you.
Take the A, B, F, Z out.
Yes, good. So this one's pretty straightforward. I'm going to show you subtraction problems now. So this is weird. This is not subtraction like we're used to. This is set subtraction. So you're actually just taking elements away, correct? So if I start with the universe and I take out everything in A, I'm left with, what am I left with? W, X, Y, M, N. Now let me ask you a weirder question. What is A minus B? Why is that a weird question? There's more in B than there is in A. So here's how set subtraction works. Set subtraction? What's in here? Do I need more or less? I don't know. Set subtraction is not like numerical subtraction. I don't care if there's more. I just take out any element that's in this. I take it away from this. So what element is in B that's also in A? Well, we actually know that already, don't we?
Yeah.
So if I take these out of A, what am I left with? A and F. There we go. So set subtraction is not really exactly the same as numerical subtraction, right? You guys with me? So it doesn't matter that B has this other stuff in it. All I care about is whatever's in B, I want to get out of A. Okay, maybe let me stop for a minute. All right. So it's sort of like me saying, I want to take out of this class, I want to remove anybody who drives a Hyundai, right? Are there more Grossmont students who drive Hyundais than are in this classroom right now? Yes, but I don't care about them. I just need the ones out of this class that are that. Does that make sense? So the other students who drive Hyundais are these guys, and this guy, right? I don't care about. I just want the ones that are in my class who match this set out, right? I don't really. In case you drive a Hyundai, you're fine. Yes.
Why isn't it AFW? I guess.
Where did I leave? Oh no. Why would it be? So I want to start with set A, and I want to take out anything that's also in
It's
B.
not, so it'd be, I'm thinking of B minus A.
Yeah, what would B minus A be? Start with everything in B and take out anything that's in A.
In that specific problem, we're not worried about the universe at all, right?
Not worry about the universe at all. Yeah, W, X, Y. Because you took out B and Z because they're in A. So set subtraction just says, take out any elements that are in the first dude and in the second dude. Take them out. Okay, maybe. You don't care about the stuff in the second dude that's not in the first dude. You don't care about those. They're already out, right? Maybe. Okay. So coming back to something that cares about the universe, right? There's the idea of complement. the complement of A. There's I don't know if you guys, let me see if you guys remember this. In geometry, there's something called complementary angles. Do you guys remember what that is? So if I say one angle is 20, the complementary angle is what it's needed to make it a right angle, so it'd be 70. So in this case, the complement of A is everything A is missing that would make it the universe. So what is A missing that would make it the universe?
W, X, Y, M, N.
Yeah, W, X, Y, M, N, exactly. Yes?
I just want to clarify, so U is always gonna be the universe symbol? That one?
Yeah, I'm always going to use U, and so is the book. Will be
Okay.
universe. Yeah. Okay, I like it. In like statistics, we normally consider that to be the population, right? You with me? So you've heard the word population before, right? And then from a population, you take a sample. So this is like a population, and there's two different samples I could take, right? Two different subsets. All right. Oh yeah, okay. So yeah, visually. Let's say I had this. Could you shade in that? Shade in, don't say anything, just try to shade in. So draw that picture. Can you shade in universe minus A? What did you do today, honey? I subtracted A from the universe. What did you do? So if I said shade in the universe, wouldn't you just shade in the whole damn box?
Minus A.
If I say universe minus A, you just don't shade in what? The A circle. So this would be, that would be universe minus A, yes?
Because A and B are a part of this universe.
Yeah, A is its own circle. It just happens to overlap with B in this case, right? So we could talk about the overlap in certain ways, but A is its own damn circle. The people that like apples, right? Some of them just happen to also like bananas. So we took the universe and we're like, all those apple-loving freaks, get rid of them. This is not my stance, by the way, but sorry, you can stay. What's up?
Which is what is shade in the intersection?
No, because what circle is the intersection in? It's a weird question. A and B. And I want to throw everything out that's in A. So that intersection is in A, it's gotta go.
And that's just the B people that like apples, so they get to stay. Right? That other B is kind of like in A's territory, so they get to stay.
This is out. Anybody in A has gotta go.
That's, yeah.
The shading. Does any of the shading include people that like apples? Nope, so we're good. I want the universe and I want to take away all the apple-loving people. It's a very strange way this lecture has gone, but it's okay. Deal with those freaky people. What about, how does that relate to a complement? What does a complement mean again? If I wanted you to shade in a complement, would it be different from this? Because here's a circle A, correct? A complement, I would want you to shade in everything that would make the whole A the universe. Isn't that the same damn thing? Okay, cool. So the universe minus A equals a complement. Yes? That's generally true. Okay, I like it. We might keep. Now, let me focus on some numerical problems you'll see with Venn diagrams. Okay. Let's pick some different letters. W and M. Watermelons and mangoes. Okay. I want something about fruit today. I'm going to throw some numbers in here. Those are number of people. So let me ask you this first question. How many people like both watermelons and mangoes in this group? Two people. So watermelons and mangoes, the number in that group is 2. How many people like watermelon?
No.
7.
Is the two people
Oh, yeah.
section.
I picked bad numbers because we're not talking about that 9, correct? How many people are in this circle? 9. Good. Everybody see that? So the number that like watermelons is 9. How many people like mangoes? 11. Kick ass.
Is hard.
Are you guys with me so far? It gets a little weird because if you're in the intersection, you are also in each circle. So I wouldn't say only 9 people like mangoes because those 2 also like mangoes. So 11 people like mangoes. Are you with me? So in the homework, you're going to have to be able to do it this way, and you're going to have to be able to create a Venn diagram from them telling you this stuff here. Are you guys kind of with me?
Oh, like a curly backwards.
Yeah, but you're going to start with this, and you have to draw the picture and put the numbers in. Always exciting. Does this number show up anywhere explicitly? Where does this number show up?
If you add.
In the M circle, but part of it has been cut in parts, right? Okay. How many people don't like watermelons or mangoes in this group? 3 people don't like watermelons or mangoes. So that would be, there's a few different ways you can do this, but I could do universe minus watermelon and mango. Or mango, and that would be 3 people don't like either one. Okay. How freaky do they get? Oh, not too bad. Okay. Some of the homework gets interesting. We do one more example of this. I think some of you guys are going to really enjoy this one. Let's see. Oh man, I need some new markers. Right, now you're like, come on. Can somebody please tell me what this is in symbols? Those people are in which circle? So how would you write it kind of mathematically in set notation?
Is that A instruction of set on B and C?
Yes.
Sorry, I don't know the name of the shape.
Intersection, yeah.
Intersection.
You got it. So if I say what circle are those people in, you say in circle A and B and C. A and B and C. Okay. What about these people? Say it again.
A and C.
A and C, kick ass, right? Okay. So there's going to be a few homework problems where they have either shaded in or numbered, and you have to identify an expression that tells you what that piece is. Yes?
How are those people not? Oh, because you only shoot it in the. But
Yeah, the
the
first-
outline that B circle real quick, how are they not in B?
So here's the B circle, right?
Yeah.
Oh, I see what you mean.
Yeah, no,
A, B, C is.
that would still be ABC.
This is
Did you just
A and it meets with C, right? So it's A and C, correct? Does that leave B out somehow? Did I say anything about leaving anybody in B out? No. So, let me ask you, this person right there, are they in circle A?
Yes.
Are they in circle C?
Yeah.
So are they in circle A and C?
Yes.
So saying this, does it throw B people out? No.
So that is acceptable. Well, what if
Totally.
we put A, B, C? That's not, is that not?
If you say A and B and C, you're not just talking about this part now, you're talking about this tiny little piece. Yeah. You've made it too specific.
Oh, because
Right.
that part is only A and C.
Well, let me ask you this. I wish I had another color, but I didn't have too bad. Here, I shade this in. What is that?
Just B.
That's B, correct? Right? That's B. Is anybody concerned that I didn't say anything about C? Because isn't that part in C? Do you see how that doesn't matter? If I just say that is everybody who's in circle B, that's all I need to say, because that's everybody in circle B. Some happen to be in C. Who cares? So if I say this, what's that? That would be B and C. I like it. How much have you guys worked with Venn diagrams before? You've seen them before, I'm almost certain, but you might not have worked with them, especially not like this. Okay. Yeah.
What did you say, is there a way to write the B that you just filled in?
So which one, sorry?
The one with the wider lines. B. The one on the corner.
Oh, this guy.
Yeah, how do you write that one?
Oh, that is B.
Oh.
Yep. I really want you to. Does circle B happen to hit other circles?
Yes.
Yep. Do I care? The how do I define all the people I just shaded in? They're in circle B. Are some of them in C? Yeah. Do you need to tell me that? No. If I just said, I see a bunch of dogs on the volleyball court, could some of them be beagles? The fact that it didn't say they're beagles, does that mean they can't be beagles? No, they're dogs. Sure, there's overlap with other types of dogs. I don't have to say that just to say there's dogs out there. Right, you didn't say beagles. Oh, sorry. You didn't say basset hounds. Oh, I'm sorry. You see what I'm saying? So this is what's happening here. What's the quickest way just to identify these people? They're in circle B. That's all I'm gonna say. Okay. I like it. Yes.
Well, then, for like the middle one that includes all three of them, why wouldn't you just say this is A? Because it is A.
And it's B and it's C. If I say A, then that means circle A. Yes?
But it's in circle A.
But because it's all, isn't it,
No,
because
no.
it's only part of circle A, that's. why
If
it's
I want specifically these, I want specifically that, right? I can't just say A because A is all of circle A.
Is it because,
Wait, then what are you talking about right now with the A and
is
C?
it because you're
What's part?
specifically shading one?
Okay. Yeah, let me move to the overhead because my markers are dying. Slow deaths. Let's see. Do I have enough paper? Yes, I have some paper.
When do you upload those, Mr. Bowles?
They're up. All of the ones I've done so far are up. And the link to YouTube is up on Canvas. My username is WallersMe. If you want to go watch another video and go, maybe the second viewing will make sense. Let's see. Alright, let's see. There we go. Okay. Alright, so. Let's see. So at least now we can see something. Oh shit. Just trace my finger down there. Alright. I don't know if I can be specific with these lights. Does that do anything? I love the light system here. Nothing. That's useful. Alright. You guys good out there? I don't know if I can get anything in between. Alright. Let's just look at this. If I only want this, if I want to describe to somebody just those people, if I say, yeah, those are circle A people, Does that description include more than I should have said? Circle A people. Is that a circle A person right here? Is this person right here a circle A person?
Yes.
Yes! So that's more, that I can't just say circle A if I want to talk about just these people. Where are those people?
In B and C.
They're in A and B and C. They're in the intersection of all three. Do you see what I mean? So that's how I would describe this location, is it's the intersection of all three circles. Okay. If I wanted to talk about this, those people, where are those people? Those people are in what circles? That is exactly how you would describe them mathematically. Does B even matter?
No.
At the moment? No. Some of them are B and some of them aren't. Who cares? How would I describe to somebody that group of people? They're the people that like apples and cherries or whatever, right? Does that make sense? This is certainly the intersection between circle A and circle C, yes? Okay, I like it. Now let me see if I can backtrack to here. If I intersected that with B, then that would just be this piece. What's the intersection between these people and B? Isn't it just this piece? Which is another way to see why this answer includes all three. What if I ask you to shade in circle A? Just shade in circle A. Wouldn't you just shade in like that? So that is A. Does it happen to intersect with other circles? Does that matter in describing what group of people I'm talking about? No. Do you see what I'm saying? If I say 18-year-olds, do you have a vision in mind? Some of you guys might be in that group. I don't know. You guys with me? Some of you guys might have that group very far in your rearview mirror like me. Right? So can you see 18-year-olds in your head? Can you see a group of 18-year-olds? Do some of them have blonde hair? Does it matter if I'm just saying, how old are these kids? They're 18-year-olds. Do they have blonde hair? Well, who cares? Do you see what I'm saying? So it's all that matters is the most direct way to describe what we're talking about. So this would be group A. This would be people that are in group A and group C. Because that is definitely the intersection between those two circles, correct? Okay, maybe not, maybe so. So, where on this picture, don't say anything, try to draw this picture, where is B and C? Don't say anything, just shade in B and C. Who's got that? Can you describe to me or some?
Is the region in between B and C without A?
Oh, just this year?
Yes.
No.
No?
You include the entire.
What do you mean?
Yeah.
Is this person right there? Are they in circle B and C?
Yes.
Yep. So they should get included. Yeah.
Oh, I messed up. Okay.
Now, just to go off of what you just said. If I did want just this, right? Can you see, am I up there? Yeah. If I did want just this, that's less than B and C, correct?
Yeah.
That's B and C minus, there we go. Right? The more specific of a slice I want, the more elements I need to describe it, yeah.
How does the PEMDAS work for sets? Thankfully, this class does not include a dive into set algebra. There's actually a whole class you can take about set algebra.
So how do I avoid that?
Oh, well, you should be able to avoid it pretty easily. It's one you have to seek out. You're not gonna accidentally enroll in set algebra class. If you do, come see me and I'll apologize. Okay. So I wanna do one specific example. So let's say, there are 23 people in A and B. There are 28 people in A, and there are 40 people in B. And then I want to say that there's a total of, what you got, Jeff? There's a total of 70 people. Why does that look so good? Oh yeah, that's right. Yeah. So this is an example of a problem you gotta go backwards. So you have to draw this picture. Well, how many circles do I need? I just need two. Where do you think I should start?
With the universe.
Not with the universe, no.
With B.
I need to start the innermost. So how many are in A and B?
28 and 40.
No. How many are in A and B?
23.
23. So where's 23 have to go? How many have I already put down in circle A? I've already put some people down in circle A, yes? How many? I've already drawn people in circle A in my picture. How many?
23.
I've already got 23 people in circle A, yes? How many people did I say is total in A?
28. So you got to try.
So how many do I put up here? 5. You guys see that?
Yeah.
Every problem where they do the Venn diagram backwards, they give you numbers and you're supposed to draw, you start at the innermost. Because that means you've already put some in every circle. Then you kind of work out from there. How many do I put over in the side in B?
17.
Good, because there's 40 total. So I need 17 here. How many people is that total so far? 17 plus 23 is 40 plus 5 is 45. Good, so 25 is out here.
I'm sorry, how did you get that? 17? It was subtracting.
Oh, how many does it say is supposed to be in B total? How many is supposed to be in B total? 40. How many did I have up there already? 23. So it must be 17 to make 40 total people in B. Do you guys all see that? How many people are in the B circle? 40. Exactly what it's supposed to be. How many people are in the A circle? 28. Maybe. And how did I get this number on the outside? I just add, and then whatever's left over to make this, that's what's out there in the universe. I like it. Those are the people that don't like apples or bananas. Okay. Alright, yes.
I'm a little confused with how you got to 25.
Oh, again, those are 17 people.
Yeah.
Plus 23 people, that's 40.
Okay.
Plus 5, there's 45 total people up here. Because you don't want to count those people twice.
Okay,
You see, you
that's
never
what I was
do
doing.
40 plus 28 because I counted 23 people twice, didn't I?
Yeah.
Do you see that?
Yeah.
Okay. So you can't really tell how many people there are so far until you get this totally done. 45 people total, 25 more to make 70, so there must be 25 out there just floating in the universe. Yeah. Okay. I like it. Okay. What time is it? Okay, good. So I'm gonna let you guys get in there and try that. Venn diagram is just a part of the homework, but it's in there. Make sure I didn't miss anybody. Oh yeah, there's one more idea. That's right. One more idea in section 2.1. So, do you guys know when you took algebra and you had to graph points and such, did you make an XY plane, right? Do you guys know the official name of that XY plane? It was named after this dude, Rene Descartes. It's called a Cartesian plane. You guys ever heard that before? So there's like, there's some urban legends in math, none of which would make a good movie. But supposedly Rene Descartes was sick in bed, looking at the ceiling, and he saw a little fly, and he's like, I can describe where that fly is using an X and a Y axis. So that's the urban legend. So for us right now, there is something called a Cartesian product. And all that is if A is 1, 2, and B is a C, for example, the Cartesian product of those two things is just all the pairs you can make. So, for example, I can make 1A, kind of like a point on an XY plane. What other point can I make?
A1.
That's the same thing.
Okay.
Yeah. So using this first and this second, what other point can I make? I can make 1
23C.
C. 23. Oh, these are horrible brackets, right? These are two sets. So this will be, so I can make 1A, I can make 1C. What else? 2A,
2C.
2C. How big is set A? How big is set B?
2.
What's 2 times 2? 4. Set A cross B is 4. This actually is related to why we use the X for times. It's actually something called a cross product. It's got a larger idea than what we think, but this is a really basic. So if I had a, let me do this real quick. If I had a set A like 1, 2, 3, and set B was W, Y, what would A times B Cartesian product be? It would be 1W, sorry, 1Y, 2W, 2Y, 3W,
You
3.
just keep going down, like following along.
Yeah, so sort of like this is the input, this is the output. How many points can you make? You can make points 1 with this and this, so there's 2 points there. How big is this set?
3.
How big is this set?
2.
3 times 2 is 6. How big is this set? 6. Hey. So that's kind of like where the idea of our multiplication came from, to be honest. Yeah.
And again, it doesn't have to be in order, but does that still have to be in order?
Well, it's kind of important that if I did B times A instead, B's would be first and these would be second. Do you see what I mean?
For this simple people, yes, they should be.
Yeah, so the stuff from A has to be first in the point, yeah. I like it. Okay, I like it. All right. Yeah, sure. Okay. So so we're gonna do a little bit out of section 2.2, and then we'll go on our little tour and we'll call it a day. And on Tuesday, I'll bring kind of like a little group worksheet to kind of practice everything we've done so far. It'll also serve as a little practice for our first quiz, which I don't think, we'll probably have it, a week from Tuesday, I think, because I want to give us enough time to get enough stuff to have on the first quiz. So I just want to do a little bit out of section 2.2. We've already talked about kind of the beginning of section 2.2. I run out of paper, so I'm going to go back on the board for a bit. Okay. The lights are like, technically I turned on.
Flashback.
That is really on. Oh, are you dead?